So today we're going to introduce the topic that's referred to as analysis of variance or ANOVA. And this is basically an extension of many of the two sample tests that we've talked about over the preceding weeks and lectures. And so we'll start with just a big picture review. There are some natural analogies, as I had mentioned, to parametric tests like the t-tests. And so we'll present one-way ANOVA today, which means we're basically considering the influence of one independent variable and how that may affect a dependent variable of interest, specifically when that independent variable can be used to break our data set into a series of homogeneous groups. A couple quick notes regarding short-term deliverables. And so I compared where we're at currently to what the schedule is. And I've obviously, if you've looked at the syllabus, I've shifted things around quite a bit. And so we're significantly behind what was initially proposed there, but I focus more on some of the fundamental aspects. So just as an aside, we'll be pushing back the deadlines for the next two deliverables. And so the lit review will be due now on March 5th and assignment 3 will be due on March 12th. And that would be the last assignment before the midterm. So just an FYI, and details of the term paper review, I've got some slides that I'll be posting and providing on Wednesday for that. And then assignment 3 will go through ANOVA and also an introduction to simple linear regression. Okay. All right, and so at the end of today's lecture, you should hopefully be familiar with analysis of variance and how it works both conceptually, so in terms of how we take the total variability that we're observing in our dependent variable, and then we try to determine how much of that variability can be quantified by some independent variables of interest versus how much of that is just pure random noise or error. And from that understanding, you should then be able to conduct a one-way or single factor analysis of variance or ANOVA. So the data we're going to be working with today are modified and based upon a study we had conducted for the Michigan DOT probably about 10 to 15 years ago now at this point, where we helped to evaluate the impacts of a statewide installation program for centerline and shoulder rumble strips. And so you're probably familiar with rumble strips. They're basically indentations that are milled into the pavement, which provide an alert to drivers to let them know that they're about to depart from the travel lane. And so they provide an audible rumbling sound, hence the name, and then also a tactile alert that drivers feel as they're crossing over either the center line or the edge line. And there are several unintended consequences associated with their installation. And so while they improve safety significantly, they do tend to generate noise, and that noise can be problematic for residents and businesses and others who are located on or near the roadways where these rumble strips are installed, okay? And so what we had done as a part of this study was basically collect noise data for rumble strips that had been milled at different levels of depth, with the hope here being that we could try to determine if there was a specific range of depths that would be appropriate such that we could minimize sound impacts and noise impacts while still maintaining the functionality from a safety perspective. And so to that end, we collected data from a number of states throughout Michigan, and we'll see that summarized right here. So we basically have 12 noise measurements. Now, actually, there's significantly more data behind the scene here. So we actually had conducted a series of test runs at each of these locations. We used the noise meter to measure the maximum noise that would occur when one of our student drivers would basically drive over the rumble strip, and we try to see how much noise would be generated as a consequence. And so we went through a number of replicates at each of the individual locations, and what you see in the table here are a series of the average peak noise levels that were experienced during those runs, okay? And so you'll notice we're providing details regarding the highway where the data was collected. There are two sites, so M57 and M72. We actually had two different locations that were separated by differences of miles in those cases on M57 and M72. And you'll notice what we've done here is we've grouped these highways into similar ranges based upon how deep the rumble strips were at each of these individual locations, okay? So basically those depths ranged from 0.4375 up to 0.5 or more inches. And so we're looking at ranges of depths here, and there's some level of imprecision in terms of how these are milled, and so we set some various thresholds here, some of which were based upon existing MDOT policies in terms of what these depth ranges should be, okay? So we basically have a variable here, rumble strip depth, which we're interested in what the impacts of that variable are on peak noise. And so as an example, we could compare the noise between these groups using a series of t-tests, as we've talked about in some of the prior lectures. And so that's actually where we're going to start with this. And so what we see right here, for each of these individual groups, we can calculate what the average noise levels are, and we can also calculate the standard deviation of those respective noise levels. And so that information is all presented right here. And so the first group of sites, so this would be the groups that had the lowest rumble strip depths, showed average noise levels of 77.7 decibels. The second group, which ranged from 0.4375 up to 0.5 inches, measured 79.78 decibels. And then the group that was above half inch in depth measured an average of 85.43 decibels. And so you see, it looks like there does appear to be some increasing effect in those noise levels across these groups. And we're also provided with estimates of the standard deviation of those noise levels. And those range from 0.55 to 1.8 decibels. And so we do see an increasing trend there, although by various tests, these weren't shown to be statistically significant, just as an aside here, okay? And so if we wanted to, we could basically conduct a series of t-tests that would compare these respective conditions to one another, okay? And so as I had indicated, we've basically established each of these into the three groups we see indicated there. And to calculate, we'll work with students' t-tests, again, because those variances weren't significantly different from one another. And so consequently, in this instance, since we've got equal sample sizes of 4 sites in each of the 3 groups, this will end up being just a straight line arithmetic average of the variances within each of those respective samples. And so the pooled variance when comparing group 1 to group 2 is going to be 0.98. Comparing 1 to 3, we would have 1.76. And then comparing 2 to 3, we would have 2.43, okay? And so keep in mind here, the prior slide presented standard deviations, and so I'm squaring those respective quantities when I'm going through and conducting these respective calculations, okay? All right, and so what we can then do in each of these instances is we can calculate students' t-test. And so in doing so, comparing group 1 to group 2, we see a t-statistic of negative 2.98. Comparing 1 to 3, we see a larger t-statistic of negative 8.23. And then lastly, comparing the second and third groups, we see a t-statistic of negative 5.13. Okay. And now keep in mind when we determine the corresponding critical value in this case, so we're dealing with students' tests. In this instance, we'll work with this as if it's a two-sided hypothesis of interest here. We're interested in higher noise levels, but here we're just assessing whether there's a difference one way or the other. And so consequently, in this setting, we're going to select a critical t-value at alpha of 0.025. And that again is just because we're conducting this as a two-sided test. Our degrees of freedom here, as you'll recall, are going to be N1 plus N2 minus 2. And so 4 plus 4 minus 2 gives us 6. And consequently, our critical value is going to be plus or minus 2.447. And as you can tell from each of these individual tests, we're going to reject the null in each instance. And what that would basically tell us is that we're finding that we see significant differences between each of those respective groups. Okay, so it appears that depth does make an impact on noise, and to that end, we're consistently seeing that as our depths get larger, our noise levels get higher as a consequence. Okay. Now, there are a few concerns that arise here conceptually from an analysis standpoint. And so the big one there is we're conducting repeated comparisons here. And so we've started at a significance level of 0.05. And so if we think about that, what's the probability that we would commit a type 1 error in any one of these tests? So if we set our alpha at 0.05, what's the probability we'd commit a type 1 error? Yeah, it's just going to be 5%, right? Thanks, Jesse. And so 5% in any one of these tests, but since we're conducting 3 tests, in this case, 3 comparisons to explicitly examine differences between the 2 groups, each of those individual comparisons has basically a 5% chance of being wrong. Now, if we think about the correlation between the data here, the numbers might not be quite so extreme that we'd have a 15% chance, but we do know that our likelihood of making an error is going to be significantly greater than 5, just based upon the underlying probability and statistics, okay? And so that provides motivation for what we'll refer to as analysis of variance, or ANOVA. And so just to get a sense from the audience, could you raise your hand or give me the thumbs up just if you have some familiarity with ANOVA? Okay, I see a relatively small sample at this point. Do any of you recall using ANOVA within the context that we're talking about here? Not specifically pavement noise necessarily, but okay, not a lot of coverage there at all, or my audio is poor, or you don't want me to ask you a question, but that's all fair. So with that, in analysis of variance, as I had alluded to on the preceding slide, when we're comparing more than 2 groups, each of these individual tests presents the possibility of either a type 1 error, where we would, in this context, we'd claim a difference in noise due to the rumble strip depth when in fact there isn't one, or a type 2 error where we'd actually miss that fact altogether just because we were either unlucky with how we sampled or our sample sizes weren't sufficiently large. And so consequently, each of these comparisons has the same likelihood based on our pre-specified significance level of rejecting the null when it's actually true, or failing to reject the null when in fact it's false. And so consequently, that's problematic because it was somewhat arbitrary that we made the decision to accept a 1 in 20 chance of committing a type 1 error at the onset. But I think we certainly wouldn't set up our experiments or our data collection plans such that we'd have a probability of error that was significantly larger than that. And so that's where ANOVA comes in. So analysis of variance basically allows us to simultaneously compare the means across multiple groups as a part of a single test. And we're able to do that while controlling for what we'll refer to as the family-wise error rate. And so that's basically the collective probability of us conducting and obtaining a type 1 error at some specified level of significance alpha, okay? And so what one way ANOVA, which we're going to talk about today, does is it allows us to examine differences between groups based upon one independent variable of interest. So in this case, we have noise data that's collected from a variety of pavements. We can use that pavement rumble strip depth to group each of those segments into categories. And based upon those categories, those segments are essentially homogeneous then. So we have similar ranges in terms of the depth levels, and we're able to explicitly make comparisons based upon the level of noise that's generated within those specific ranges of rumble strip depths, okay? We'll talk a little bit in the subsequent lecture about two-way ANOVA, and this basically takes the concepts we're introducing today, and then in addition to looking at the depth of the rumble strips, we could throw in a second factor, like say the pavement type or whether there's a chip seal that's used concurrently with the rumble strips. And so in that case, you might expect that depth has an influence, and so does the type of pavement and the treatment, as an example. And so in that circumstance, we could break this into even a larger number of groups. And so as we increase the number of groups, we're obviously increasing the number of comparisons between means of those groups. And as a consequence, if we just conducted t-tests as we would normally, our error rate is going to increase dramatically in these instances. Okay, and so from a big picture perspective, we're probably far enough in the course now that it'd be good for us to start introducing models. So this will be the first time we introduce an explicit model here. So if we think about the observations from an experiment, in this case, the noise measurements that are collected based upon students driving vehicles over rumble strips and then measuring the associated noise across a number of different pavement sections, we can think of that noise measurement as our dependent variable y, and we're going to subscript that each of the individual noise measurements can be represented by the quantity yij, and we can think of that in terms of the indexing structure that I've introduced here. So yij is going to be the jth observation within group I, basically, okay? So in our case, we have 3 different levels of pavement depth, and we would have I ranging from 1 to 3 consequently. Just for nomenclature here, we'll generally denote our number of groups by the letter A. And so in this case, A would be equal to 3. And then within each of those A groups, we'll have a series of J observations, and J would generally range from 1 up to N. Ideally, ANOVA works best when we have equal sample sizes. We can use these same techniques when the sample sizes are unequal, but just for demonstration purposes, we'll work with the case where we have similar sample sizes. And so in this case, we've got 3 pavement depths and we've got 4 sites within each of those. And so A is 3 and N is 4. And so if we wanted to estimate what the average noise level was at any given location, this model is basically telling us that our best estimate of that noise level at location ij is whatever the average noise level is within that group I. So whether that's the first group with the lowest pavement depth, the second group, or the third group where that pavement depth is the greatest. Our best estimate as to the level of noise we'd see at any group that fell within those ranges would be represented by μi. Now, not every site is going to show us that same result, μi, because there's a wide range of other factors that may also affect noise that we're not explicitly controlling for here. And so I used the example previously, maybe the pavement surface condition is slightly different. Maybe we're in different geographic areas and the acoustics are for some reason different on the site. Maybe there are different levels of background noise. And so all of these other factors are basically just comprising what we'll refer to as a random error term. So this will be unique to each individual site and each individual observation within those sites. And so we'll have some variability from the group mean within the groups from site to site is basically what that's telling us, okay? So from there is a natural way to extend this. We can think about that same model in an alternate nomenclature. And so here our setup is the same. We're still dealing with each individual noise measurement being y sub ij. So it's being drawn from group I, and j is the observation number. And now what you'll notice here is we've introduced a new term tau, which we're going to refer to as a treatment effect. We still have a mu here, but you'll notice this mu isn't subscripted in any form or fashion. So we're assuming this mu is basically representative of every one of those noise measurements that's being captured in this model, okay? And so we can think about all of those individual observations having the same overall mean or grand mean. And then the individual sites will have an effect that's based on their depth. So depending upon which of those 3 depth ranges we see, the noise levels within those depth ranges are going to vary from that overall mean. So some of the noise. Some of the depth groups will be larger, some of them will be smaller, and as a consequence, some of those sites will experience higher noise levels, some of them will experience smaller noise levels, but we're quantifying the differences between the sites by using these tau or treatment effects here. In addition to that, we still have the same epsilon sub ij term that we had introduced previously, and it should hopefully be straightforward from this. So this mu plus tau I is completely analogous to just using the mu i's that we had done previously, okay? So instead of us having estimates of 3 different mu i's, we have now one overall mu, and we have 3 treatment estimates that tell us how the average levels of noise within each of those 3 groups varies from that overall average across all 3 of the groups, okay? And then even within those specific 3 groups, each of the individual sites would vary among that respective group mean consequently as well, okay? And so again, just terminology, we refer to mu here as the grand mean or overall mean, and then tau is representing the effect of whatever the ith treatment is. And in this case, we basically, our 3 treatments would be the 3 different depths of pavement, okay, of rumble strips. All right, and so from a hypothesis testing perspective, what we're ultimately interested here is in evaluating whether or not the means are equal or different across these different subsets of pavement groups based upon the depths at which the rumble strips were milled. And so if we think about the initial presentation of these data, that model that's based on group means, our null hypothesis in this case would simply be that each of those individual group means were equal to one another. So in this case, the mean for the first group and the second group and the third group were all equal to one another. And then our alternate hypothesis in this case is simply that at least one of those means is different from the others. And that could mean that there's just one difference, or maybe we're comparing 10 different groups and each of those is distinct from one another. So either of those circumstances would result in us rejecting the null hypothesis. But as a starting point, we're only concerned with whether a difference exists and not which of those means happens to be significantly different than the others. We'll talk about some follow-up tests subsequently that get at that point, but at a very high level, ANOVA is evaluating that general hypothesis of interest. Okay, we can also think about this in terms of our treatment effects that would have come on the preceding slide. And so in that scenario, keep in mind, we're focused on the overall mean and how much the average noise levels within each of the groups would deviate from that overall mean. And so with that context, then we can think about these same hypotheses stated in terms of our tau or treatment effects parameter rather than the mu from the first model. And so in this case, our null is simply that each of those treatment effects is equal to one another, and more specifically, all of those treatment effects are equal to 0, which in essence would mean that this would just simply reduce to the mean noise level plus or minus whatever variation we see that would be due just to random noise, that epsilon sub ij term, okay? And so our alternate hypothesis here would simply be that we have a difference for at least one group as an example, okay? And so that gives us a setup for how we're going to proceed through our subsequent calculations, okay? And so if we think about the way our data are generated, we're going to assume that our data follow a normal distribution. And so if we look at each of the individual noise measurements or the mean speeds from the individual sites, we characterize those as being normally distributed, and their mean would be equal to whatever that overall mean is, plus the associated treatment effect that would be unique to which of the 3 groups each of those red segments was included in. And then the variability or the variance of those data would tend to follow a normal distribution as indicated by sigma squared here, okay? And we also assume that the error terms associated with that model, the epsilon sub ij, are also normally distributed random variables. And we'll assume they have a mean of 0, which in short here would basically mean that the individual data points would tend to be clustered around this group mean that's denoted as mu plus tau I. and they would be denoted and they would disperse around that mean with variance sigma squared, okay? So we can think about sigma squared from those two different perspectives there. And as one aside, we're going to assume that that variance is constant for all levels of the factor. And so what does that mean in practical terms? Well, this is similar to when we're looking at whether students or Welch's t-test is going to be an appropriate analysis framework. And so you'll recall in students t, we assume that the variances were equal across our groups. Likewise, in the case of ANOVA, we're going to assume that the variance is again relatively equal across our groups. If it's not, there are some non-parametric alternatives, most principally the Kruskal-Wallis test, which we'll likely not get into at any great detail here, but I just wanted to make everyone aware that there are non-parametric alternatives to ANOVA as well. And so if we think about the overall setup here from a big picture perspective in terms of the analysis, what we're basically going to do is take the variance of our data and we're going to decompose it into its constituent parts. And so as a starting point, if we look at the total variability in our dependent variable, in this case, our noise data, we can think about that quantity, which we'll denote as our total sum of squares. So we see SS sub t, so the SS stands for sum of squares. The t subscript means we're talking about the total sum of squares. And this is basically a measure of the overall variability that's present in our data set. And this should look very familiar to everyone. And so what you'll see here, we take each individual site's noise data within each of those respective groups, and we take its difference with respect to the mean. Now, just some quick nomenclature here. We see a Y bar and you see some dots as subscripts. And so each of these dots means that we're averaging over that specific index. And so for example, within each I, we're averaging over all J's. And then within the entire sample, we're averaging over each of the individual treatments as well. And so that just basically means this is the average noise level across all of those 12 observations that were presented to us previously. Okay, and so we take that sum of squares difference of each individual data point from the overall mean, we add it within each of our groups, and then we add it across each of those groups. And so this is basically just the numerator of our sample variance calculation. And so after a little bit of algebra, we'll see that we can take that total sum of squares and we can basically partition it into two distinct parts, okay? And so work with me here. You'll see on the left, this is our total sum of squares that was presented on the preceding slide. And all we're doing here is we're breaking this into two component parts, okay? And we'll refer to those generally as the sum of squares for the treatment and the sum of squares for the error. And if you look at these quantities, what you'll notice is we're taking this difference. So basically we're measuring the distance of each individual data point from the overall mean, okay? And we're breaking that into two parts. First of all, the difference between each individual data point and its group mean. So you'll see here, we're taking each point, taking the difference from Y sub I, which means the average within that same group, and we're averaging over each of the 4 observations that occurs within that respective group. And so that's one portion of that difference. And then the second portion is whatever the difference is between that group mean, denoted here, and that overall mean. And so it should be obvious here from construction that if we take these two quantities and add them together, that would basically just give us this back, right? So we would take this term minus this term plus this term minus this term gives us our total sum of squares term here, okay? And this is useful because it allows us to think about where the majority of that variance is arising from. And this will become more evident on some of the subsequent slides here. So just quickly, an alternate way of us specifying that. So this is identical with one minor exception here. You'll notice that we've pulled an N out. And in this case, we're just summing this quantity across and within each of our respective groups, and then multiplying by our corresponding sample size, again, assuming that we have equal sample sizes here. And the reason we're doing that is because in each of these groups, neither of these quantities are changing. So it's as if we're just calculating that same quantity n number of times, okay? And then lastly, from a big picture perspective, this is just showing us nominally what these respective sums of squares represent. And so the total variability in our data set is a function of two things. One of which is any observable systemic difference that occurs between those individual groups, as you see here. And then the part of that that's just basically random error or noise, which would be the degree to which those individual data points are clustered or the degree to which they vary across their respective group mean, okay? And what we'll tend to see here is if there is in fact an effect of that grouping variable, this quantity will tend to be relatively large relative to this quantity, as we'll detail subsequently. Okay, and so again, another way of thinking about that is the sum of squares for the treatments is basically telling us how much variability is occurring between the different treatments. And our error sum of squares, in contrast, is giving us an assessment of how much variability is occurring within those treatments. And so continuing on that point, the ANOVA identity basically provides us with two distinct estimates of sigma squared, so the total variability that would be underlying to our noise generating process here. One of those is just based upon the variability that occurs within treatments. And so this is just the natural underlying noise that's due to site-specific factors that we aren't observing. So all of the other things in this case, besides the depth of the rumble strip, that are impacting the level of noise that's generated. And then secondly, the actual systemic variability that's occurring between treatments, which in this case would be reflecting the effects of the increase in rumble strip depth and how that would tend to influence our noise measurements, okay? And so if there are no differences in those respective treatment means, i.e. if the depth of the rumble strips doesn't have an impact, then we'd expect to see that these estimates would be relatively similar to one another. In contrast, if we find that that treatment sum of squares is large relative to the error sum of squares, then we could conclude that that difference would presumably be due to some actual effect or impact of the treatment. All right, and so if we think about this, it probably is easiest to step through this graphically. And so here we're just going to demonstrate a case where we've derived some pavement data for the case where the means aren't really that different from one another, okay? And so looking at this plot, we have a peak noise level of around 81 decibels, and we'll notice that these points are roughly clustered around that overall mean, which is shown by this big green bar here, okay? There are a series of smaller green bars that are representative of these individual group means within each of our three samples of interest. But what we're basically seeing here, if we take the difference of these individual points from their respective group means, those are relatively similar as the distance of each of these individual points from the overall mean as indicated here. And so what that means in essence is that we're really not seeing any sort of systemic effect here. And if we were to take the differences of these points about their individual means versus the difference between these group means and the overall means, those quantities are going to be relatively similar to one another, okay? Now, in contrast, the data that we're actually working with here, which were based on some field studies, look more like this, okay? And what we can tell in this case, if we take the distance between the group means and the overall mean, you'll notice these differences tend to be relatively large, whereas the differences and the distances between the individual noise measurements and their respective group means tend to be relatively small. And so just from this snapshot, it should be relatively evident that the preceding slides were showing significantly less of a treatment effect as compared to this slide, okay? And so in decomposing our sum of squares, let's get some terminology out of the way. So we have a total of A different factor levels, and within each of those factor levels, we have lowercase n observations. And so our total sample size here is just going to be equal to lowercase a times lowercase n, which we'll denote as capital N total observations. And this is again working under the assumption that we have equal sample sizes within each of those groups. And if we think about this, this is very similar to our variance calculation. And so we know from that total sum of squares quantity where we take each of those y sub ij's, subtract off the mean, square it, and then sum that, we'll have n minus 1 degrees of freedom, which in turn means we would need at least 2 observations in which to calculate that quantity. In this case, that will actually get a bit larger than that, obviously, because if we're dealing with multiple groups, each of those individual groups must also have at least 2 observations, as we'll get to subsequently. Okay? To that end, there are A levels of the factor or A treatment means, and in the example that we're working with right here, we know that A is equal to 3, which basically means that we have 3 groups. And so as a consequence, we can look at that sum of squares for the treatments term, and that basically has A minus 1 degrees of freedom associated with it, which means in order for us to calculate the sum of squares for the treatment, we'd need at least 2 groups. Of course, it really wouldn't make sense to conduct an analysis of variance with just the one group, but we can easily expand this to 3 or 4 or 5 groups. But for each of those cases, we would basically lose 1 degree of freedom, and this gives us a sense as to how the power of our test will tend to vary as our sample sizes get larger, okay? And then within any of these treatments, in any of the factor levels, there are n replicates. And so each of those n replicates would have n minus 1 degrees of freedom, which to my preceding point means that we would need at least 2 groups. And this point tells us we would need at least 2 observations within each of those groups with which to try to estimate the experimental error or the noise that's generated within those respective groups, okay? And so in total, we have A times n minus 1, or an minus a, which we'll just reduce down to n minus a, and that's the number of degrees of freedom that are associated with our error sum of squares term, or SSE. All right, and so from that, we basically have 3 different variance estimates that we're working with. And if you recall back to some subsequent lectures, when we take a sum of squares or we take an estimate of a sample variance and take the ratio of that sample variance to the population variance that it's being used to estimate, we know that that resulting test statistic is going to be distributed as chi-squared, okay? In our setting, the sum of squares for the treatment, of which there are A, is going to have A minus 1 degrees of freedom associated with it. And so our sum of squares of treatment has that degrees of freedom. Our error sum of squares is also going to be distributed as chi-squared. And as noted on the preceding slide, there are n minus a degrees of freedom associated with SSE. And then lastly, our total sum of squares is also going to be chi-squared distributed, and it will have capital N, which again is lowercase a times lowercase n, minus 1 degrees of freedom, which would be 11 in our case. All right. And so interestingly, as you may recall from the F test or the preceding, those chi-squared tests are appropriate for use when we're looking at an individual sample variance and comparing that to some reference value. In the case where we're taking one chi-squared variable and dividing it by another chi-squared variable, that is going to be distributed as an F statistic, as we had talked about previously when we compared the variances across 2 different samples, okay? And so within our context, our F test is simply going to be equal to the sum of the squares for our treatment divided by A minus 1, which is its associated degrees of freedom, over the sum of squares for our error divided by its associated degrees of freedom, okay? And so the numerator and the denominator here, what they're basically representing is the average amount of variability that's occurring across our treatments or between our treatments on the top versus the variability that's occurring within our treatments on the bottom, okay? And we'll refer to these terms generally as the mean squares, or MS, for the treatments, and the mean squares, or MS, for our error term, okay? And interestingly, if we think about this in concept, under our null hypothesis, we would know that we would tend to see the same means between each of our individual groups, which means that our sum of squares of our treatment would tend to be very small compared to the sum of squares for our error. And so the minimum value that we could observe for F is 1. And the larger that value is, the further we are from 1, or the more greater we are than 1, the more evidence we would have to refute our null hypothesis, okay? And so if we were actually able to measure the true variances, that quantity would simply be equal to n times sigma squared for the treatments over sigma squared for our error term. But instead, we're approximating that with our estimates of sums of squares as detailed previously. Okay, and so what we'll find in an analysis of variance, and hopefully this table looks somewhat familiar to all of you, at the conclusion of these analyses, we will basically summarize the results of those preceding calculations in a nice, clear tabular summary. And so what we'll do here, we'll look at the total variability in our data set, and we'll break it into its two source components. And so here we'll generally include the values that correspond to our sum of squares for the treatment, the error, and the total sum of squares, which are calculated using the preceding equations. We know the associated degrees of freedom, which are just equal to the number of groups minus 1, the total number of observations minus the number of groups, and the total number of observations minus 1 for our sum of squares, treatment, error, and total, respectively. Our mean squares are calculated by just taking the corresponding sum of squares and dividing by its associated degrees of freedom. So MS treatment is just SS treatments over A minus 1, and MSE is just SSE over N minus A. And then lastly, our F statistic is just the ratio of our mean square for the treatment and divided by our mean square for the error term, okay? We would compare that then to a critical value, obtain a p-value for the associated test statistic, and compare that to our significance level alpha. And if F is greater than the corresponding critical value, or if the p-value is less than alpha, and those results would be consistent with one another, of course, we would then reject our null hypothesis. Okay? Now, keep in mind in this case that F statistic is looking at the mean square for our treatment divided by our mean square for our error. And so MS treatment, as you recall, has A minus 1 degrees of freedom associated with it. And so that would determine where the numerator comes from in this critical F table. And our denominator is going to be capital N minus A. And so we would read down until we found that corresponding value, and then we would read across. And that's how we would determine our critical value that we would then compare against, okay? All right, so returning to the example that we had presented previously and worked through using a series of students' t-tests, we're now going to work through this briefly in an ANOVA context, okay? And so here are our underlying data. We can determine the respective quantities of interest. So here, Y sub 1 dot with a bar over it. This is just telling us what the mean noise level is for group 1, so corresponding to this first set of 4 observations. Y sub 2 bar with a dot means we're just taking the group mean for the second group of noise measurements. And similarly, Y bar sub 3 dot is the mean value of that third group, okay? And then likewise, we can calculate the overall or grand mean as Y bar sub dot dot, which is just summing each of these 12 measurements and then dividing by 4 times 3, which would be 12 in our case, which gives us an overall mean of just under 81 decibels. Okay, and that information is just shown here in summary form in the accompanying table. Okay, so having determined those respective quantities, we can now set through going through the calculations to determine our corresponding sum of squares. And so starting with our general identity here, we know that our total sum of squares is just equal to each of these individual Y sub ij's minus the grand mean, that quantity squared, summed across all 12 observations. And so I'm showing the intermediate calculations for this respective quantity here in parentheses. And so, for example, 78.5 minus 80.97, that quantity squared is what we show right here. Likewise for each of the other calculations across those three groups. And our calculated SST in this case is equal to 143.35. And so as we work through the calculations for SS treatments and SS error, you don't necessarily have to calculate each of these three quantities individually, but I would strongly encourage you to do so because that allows us for a check at the end that the calculations for SS treatments and SS error actually correspond to the same total sum of squares, okay? Continuing on, if we want to work through the calculations for SS treatment, we're simply taking each of the individual group means, subtracting off the difference from the overall mean and squaring that quantity. And so as indicated previously, that calculation is going to be the exact same for all four observations within each group. So within group 1, we're taking 77.7 minus 80.97, and that quantity squared gives us 10.67. And that occurs 4 times, likewise within each of the other two groups. And so adding up those 12 values gives us a treatment sum of squares of 127.87, which as you recall is quite large in terms of the relative proportion of SS total, which was presented on the preceding slide. And then lastly, our error sum of squares is just going to be equal to the square difference of each of these individual data points versus its own group mean, okay? And so in the case of the first observation, that's simply 78.5 minus 77.7, and that quantity squared is going to be 0.64. We go through that same calculation for each of the 4 observations within the group, and then we repeat that procedure for each of the other 2 groups. And we arrive then at a total error sum of squares of 15.48. Now from here, we can plug those corresponding values into our ANOVA table. We know our degrees of freedom for the treatment is simply going to be equal to A minus A, and in our context, A, we have 3 groups. So 3 minus 1 is going to give us 2 degrees of freedom, which we can then use to calculate our mean square for the treatment. So that's simply the ratio of our sum of squares divided by the degrees of freedom. Likewise, our error sum of squares is just going to be equal to 15.48, and the mean squared error is going to be equal to that quantity divided by n minus a, where in our case, capital N is 12. We have 3 groups, so there are 9 degrees of freedom. And that ratio is then 1.72, okay? And so then the final step in this test, our total sum of squares is 11 degrees of freedom associated with it. We're not going to go through and calculate the corresponding quantity there, although you will notice that that ratio would actually just give us the sample variance. So we'd have our total sum of squares divided by capital N minus 1. And so the final calculation here would just be calculating our F statistic, and that's simply equal to the ratio of the mean square of our treatment over the mean square for our error, which is 37.18 in our context, okay? And so the last step would be to determine whether we should accept or reject, and we could go so far as to determine the corresponding p-value, which in this case is going to be a very, very small number, less than 0.0001. Okay, and so where did that p-value come from? When we evaluate our null hypotheses at the conclusion of the test, we're going to work with our critical F table here, and we know our calculated F statistic was 37.18. Our critical value, we're assuming alpha of 0.05, and so our critical value would be the upper tail of that F distribution with A minus 1 numerator degrees of freedom. So we have 3 groups minus 1, so 2 degrees of freedom here. And in the denominator, we have a total of 12 observations. That's 4 observations in each of our 3 groups, minus the number of groups, which is 3 in this case. We'd have 9 denominator degrees of freedom. And the corresponding critical value, as you'll see here, is 4.26. We're significantly larger, ergo we will reject our null hypothesis and claim that there is at least one mean that is significantly different from each of the others. All right, and so that wraps our discussion up for today. We'll come back on Wednesday and talk about some follow-up tests. So once we've determined that there is a significant difference in at least one or more of those means versus the overall mean, there is a series of subsequent tests we can conduct in order to discern which of those means are different from one another, okay? And in addition to that, we'll also talk a little bit about the literature review for your term paper topic. Keep in mind that lit review is going to be due a week from Friday on March 5th. And then 1 week thereafter, we'll have assignment 3 due. And so with that, thank you very much for your time. And we will come back to talk more about ANOVA on Wednesday.